Okay, hello everyone again. So now I want to continue our discussion on Manning's equation. I want to talk about Manning's n, or Manning's resistant coefficient, which if you remember, we got to Manning equation from a series of experiments to find the dependence of on the hydraulic diameter RH to the power 2/3, and S naught and N. We S naught and N. We came up with that with using some momentum equation, and also assuming for very large Reynolds number, where we have where the n or the k in those equation is independent of viscosity, and is only a function of roughness of the channel and the dynamic pressure. So using all of those assumptions, as well as the assumption that the flow is uniform, we got to this equation, which is known as the Manning's equation. And Manning's equation is a very famous and widely used equation in hydraulic engineering. And it's been used for so long, and as you can see here, it's in dimensional form. Okay, unlike most of other equations that we had so far, which we are trying to do in fluid mechanics, to not dimensionalize all of the equations, so that we are not we don't all the coefficients we find are universal, are not dependent on the system of units that we use. Unlike all of those, Manning equation is a dimensional equation, and therefore the value of n, or Manning's n, depends on the units that we choose. Okay, and we don't try to non-dimensionalize this equation, although we can, because it's been widely used and you might see it in a lot of engineering applications. And so we stick to this equation, and only we change it a little bit so we can account for the conversion from SI unit to British unit and vice versa. So this equation is originally designed for SI units. Okay. So in order to do so, we define this kappa here, and we write this equation, rewrite it as kappa over n times RH to power 2/3 times S naught to power 1/2, and Q, which is the flow rate, is gonna be, as you know, it's gonna be V times A. So it's gonna be this times A, so it's gonna be kappa over n times A to power to RH, or hydraulic radius, to power 2/3 times S naught to power 1/2. Okay. So as I said, because this equation is for Manning's equation is developed for SI units. When you have a SI units and you use SI units, you just set kappa to 1, and then the reason is, as I said, n was originally the values of n are found for SI units. Okay, so the table that I'm going to show you, in which shows the different values of n as function of the type of the channel, is developed originally for SI units. And if you have British units, you just set kappa to 3.281 foot per meter to power 1/3, which is going to be 1.49. So you just set kappa to this, and then you will get velocity in terms of foot per second. And here you will get the velocity in terms of meter per second. So you just set kappa to 1.49 and set it here, and use all the British system units, and you will get the output velocity as foot per second in British units. Okay, so now let's see some of the values of Mannings coefficient n based on the type of the channel. Okay, so here you can see different values of n, which is in table 10.1 of your book. So you can see that we have a lot of different types of the channel, and as the channel becomes the friction increases or becomes rougher, you see that the value of n increases. So for example, for trees you have 0.15, for heavy brush you have 0.075, whereas when your friction or your roughness decreases, your value of n, which is function of roughness of the channel, decreases. For example, for a glass we have n equals to 0.01. So we have a lot of different materials. You can see concrete finished, concrete unfinished, wood, asphalt, trees, heavy brush, clean and straight, major rivers, weedy. So all these different type of channels have different Mannings n, and you can, based on the type of the channel, you can find the n here and set it into these equations. And by having a hydraulic radius of your channel and the area and the bottom slope, you can get the flow rate in that channel, as well as the velocity of that channel through this Mannings equation, which is kind of a semi-empirical equation in hydraulic engineering context. Okay. So this is how we get n, the Mannings n, and based on the units that we have. And now that you found this, I want to solve two examples for you. One to determine the flow rate in a open channel flow system, and the second one is going to be for finding the normal depth in open channel flow system. Okay. Let's solve the first example and look at the first example. So in this example, we want to find and determine the flow rate in this open channel flow system, and also the Freud number. And we want to know what is the Freud number in this system. So we assume we have a uniform flow, so we can use Mannings equation. The bottom slope is changing 1.4 foot drop per 1,000 foot. So per 1,000 foot we have 1.4 foot drop. The configuration of this channel is shown here. So we have the depth of the fluid is 5 foot. We have 12 foot here, and then two sides with 40 degrees. The type of the channel is new finished concrete. And so these are all the information that are given here, and we want to find what is the flow rate and Freud number in this open channel flow system. Okay, the first thing I'm going to do is I'm going to use Mannings equation, and as you can see, we have a British system here, right? We have foot, so I'm going to use the Mannings equation for BG units, British units. And so Q is 1.49, so I'm going to use kappa as 1.49 over N times A times RH, or hydraulic radius, to power 2/3 times S naught 2 over 1 to power 1/2. So let's calculate the area. The area of this channel, what is the area? So we have two parts, right? So one, we have a rectangle here. So the rectangle, the area of the rectangle is going to be 12 times 5 foot. So 12 foot times 5 foot. And then we have two triangles, right? These two triangles, the area of these two triangles, because they are the same, is going to be 2 times 1/2 times 5 foot, which is this length, times 5 over tangent of 40. So this length here is going to be 5 over tangent 40 foot. So In order to find the area, I'm going to multiply this 5 foot by 5 over tangent 40 foot times 1/2, because this is a triangle, and because we have two of those triangles, I'm going to multiply it by 2. So I get 89.8 foot square. And then the wetted perimeter, in order to find RH, or hydraulic radius, I need to know what is the wetted perimeter. So the wetted perimeter is going to be P, which is 12, which is this side, plus these two sides here. So let's see what is the area of these two sides. Okay, the length of these two sides, I'm sorry. So if this length is D, you can say that for this here, I can say that sine of 40 is defined as, so sine of 40 degree is defined as 5 over D, right? So D is gonna be 5 over sine 40, right? So this length here is gonna be sine 5 over sine 40. And then I multiply it by 2 because I have two of these lengths. And this is gonna give me the total wetted perimeter in this channel, which is gonna be 27.6 foot. So now that I have A and P, I can calculate the hydraulic radius in this open channel flow system, which is gonna be 89.8 over 27.6, which is gonna be 3.25 foot, which is less than the depth of the fluid, which is 5 foot depth. So you can see that the hydraulic radius here, the effective like depth actually, which is like the hydraulic radius in this problem, is going to be less than the depth of the fluid because we have these two additional triangles here. If we only had this rectangle here, 12 by 5 foot, the hydraulic radius would be 5 foot, right? You can calculate, you can see it here because these two terms are going to cancel if you only have this rectangle. So A over P is going to be 12 times 5 over 12, so it would be 5. So the hydraulic radius for this rectangular channel is going to be the depth of the fluid. But because we don't have a rectangular channel here, the hydraulic radius, because of these two triangles, which is kind of the effective depth of the fluid, is going to be less than the depth of the fluid, which is 5 foot. So it's going to be 3.25 foot. So the S naught, the slope of the bottom channel is given in the problem is 1.4 foot over 1,000 foot, which is going to be 0.00114. And N, Mannings N, I can find it from the table 10.1 of the book for a concrete finished, which is here, is going to be 0.012. So I just write it down here, which I found from table 10.1 of the book. And therefore, I have everything here in this equation. So I will just plug everything in. So it's going to give me 1.49 over N. N is going to be 0.012 times the area, which is 89.8 foot square, times 3.25 foot, which is the hydraulic radius, to power 2/3 times S naught, which is 0.014 to power 1/2. So this is gonna give me 915. right? So this is gonna give me 915 foot cube per second, or cubic foot per second, okay? So this is the first part of the problem. And for the second part, we want to find what is the Freud number in this channel. So the Freud number, we write the definition of the Freud number. So the definition of Freud number is V, the velocity of your channel, over a square root of Gy, which is the wave of the speed of water wave. So we can find from here Q over A is going to be 915 foot cube per second over 89.8 foot square is going to be 10.2 foot per second is the velocity of this channel. So I have everything. I just substitute everything here. 10.2 foot per second over square root of 32.2 foot per second square, which is G, times Y, which is the depth of the channel, 5 foot. Okay, so it's gonna give me 0.804. So the Freud number is about 0.8, and this shows that the channel here is in a subcritical regime, okay? Because Freud number is smaller than 1. Okay. So this was the first example. As you saw how we solved it, we just used the Mannings equation simply and plug everything in the problem to find the Q, the flow rate in this open channel flow system. Okay. In the second problem, I want to find the normal depth in this kind of open channel flow systems, and it's a little bit more tricky because we have to we will see that you have to solve a kind of nonlinear equation, like we have to find the root of a nonlinear equation. And we can do it either with trial and error like before we did, or you can solve this numerically, or just give this to a software or a calculator and find the roots in the problem. So for the same channel configuration here that we have, we want to find we want to determine the depth of the flow if Q, the flow rate, is 10 meter cube per second, and the canal lining is VD. Okay, so we have a different type of channel or canal, and also the Q is different. So Q here is 915 foot cube per second, but here is 10 meter cube per second, and we are using SI units. Okay. So again, we are going to use Mannings equation, but first we need to find the area and perimeter, weather perimeter in terms of SI units. So this is the area for these two triangles here. Y times y over tangent of 40 degrees plus one rectangle that we had. It's 12 foot times 1 meter per, this is the conversion factor, 3.281 foot, which is going to be 3.66 meter times y. So y is unknown in the problem, and we want to find it, right? Because we want to find the depth of the flow. We have to say, and we have to find what is y here. Okay. So I just write it down in terms of y. So it's going to be 1.19 y squared for this plus 3.66 y for this term. Okay. And the weathered perimeter is going to be this 12 foot, which is 3.66 meter plus two sides we had y over sine 40. Right, so this is coming from here to y over sine 40 from here. And this is going to give me 3.66 plus 3 point, yeah, 3 point, as you can see, yeah, 3.11 y meter. Okay. And then because I have A and P, I can calculate the hydraulic radius, which is going to be A over P, which will be 1.19 y squared plus 3.66 y over 3.11 y plus 3.66 meter. So this is going to be the hydraulic radius, the effective depth of this canal. And we have a weedy channel type. So from table 10.1, I can go here and see for weedy one, we have 0.03, right? N should be 0.03. And you see it here. So I just put it here. N is going to be 0.03. So I can just write down the Mannings equation. So the Q is given in the problem is going to be 10 meter cube per second equals to the Mannings equation kappa over N times A times RH to power 2/3 times S naught to 1/2 meter cube per second. So kappa is going to be 1 because I'm using the SI unit, or 0.03 times this one, the area, which is here, right? So it's going to be 1.19 y squared plus 3.66 y times the hydraulic radius, which I write it from here, is going to be 1.19 y squared plus 3.66 y over 3.11 times y plus 3.66 to power 2/3 times S naught to power 1/2. S naught is going to be the same as the previous problem. It's going to be 0.0014 to power 1/2. So you see here we have this equation, and 10 equals to this. So I can rearrange all these terms here because the only unknown here is y. And if I rearrange it, I will get to this equation. Okay, so I will get 1.19 y squared plus 3.66 y to power 5 minus 515 3.11 y plus 3.66 to power 2 is gonna be 0. Okay, I just rearranged this and I raise everything to power 3, right? So to power 3, you do this, and then you will get this equation. So this equation, as you can see, is a nonlinear equation for y. So there are many ways you can solve it, either by trial and error. So for example, by trial and error, I mean you set a y here. So you can start, let's say, with y equals to 1 meter, right? So you set y equals to 1 meter, you solve this, and then see whether you have to increase y or decrease y in order to get the correct answer. Or you can solve this numerically. For example, you can use a calculator. In your calculator, you can give this equation and ask for it to give you the roots of this equation, or through a software, computer software. And if you do that, the only physical solution, that means by physical means y should be greater than 0, and it's a real number. It's not like a complex number, right? So it's a real number, is gonna be 1.5 meter, okay? So this is gonna be the final solution of this problem. So for this type of problems where you have to determine the normal depth, what you can do is, again, we use Mannings equation, but At the end, we end up with a nonlinear equation for the flow depth. So we have to solve this by trial and error or numerically or using a calculator. Okay. So next session, I'm going to solve some more examples of Manning's equation. And after that, we are going to go through the hydraulic jump and gradually varied flow equations as the final parts of the course. Thank you very much, everyone.